Light is a fascinating and wonderful and kind of complex thing to understand. In the last several lessons, we examined light as a wave and its wavelength and its frequency and all the things about it. If you want to know more about those, there are links down there to get you caught up to speed. But we're at the point right now where we want to examine, well, light also acts like a particle. So let's explore photons and quantums and quantum energy, and let's get into kind of the crazy world of light. Here's the thing. Light has something that we call wave-particle duality. We've explored light as a wave. It is a wave. That wave is expressed in a sine function as it travels through space, but it also acts like a particle. And so we're going to focus on the particle behavior of light and try to figure out, okay, when I have this wave of light, what if I focus in on a small part of it? Just one little packet of energy of that light. How do we deal with that? Well, let's go back kind of to the beginning of the conversation about where does light come from. And I use the example of we have an atom, okay? And then we have electrons around the outside of that atom. And those electrons are perfectly fine and happy living where they are at. But if they absorb energy, if they get hit with energy, they can't live in that spot anymore. They jump to a higher energy level, which is further away from the nucleus. That's called its excited state because it's absorbed energy, and in order to hang on to that energy, it has to exist at a higher energy level. But it doesn't stay there, all right? In its excited state, it needs to go back down to its original home, its ground state. In order to go back down to the ground state, it has to get rid of the energy that it just absorbed. So it has to give energy off. That energy is electromagnetic radiation. It is light. It's visible light. It could be all the way to X-rays. It could be radio waves. It could be infrared radiation. All the different things, but it gives it off and goes back to its ground state. Okay, notice I'm showing that as a wave as it releases its energy. And so if we think about this, as long as there's still energy, let's say a tube that's giving off light in the fluorescent lights above your head, and as long as you keep the electricity on flowing through that tube, that electron isn't just going to fall and then hang out there. If it gets hit with more energy, it'll jump up and fall back down and jump up and fall back down, and this happens over and over and over. Now, I'm kind of simplifying that by showing a wave. But let's examine this. If I could turn the lights on and off really fast, like so fast that there's only one time where it jumped up and fell back down, it wouldn't be giving off a continuous wave. It'd give off one little packet of wave. That little packet of energy is called a photon. So when we think of waves of light, it's actually a whole bunch of photons, and the energy of that photon is expressed as a wave, and you have a whole bunch of them together and you end up with a wave of light. A photon then by definition is a particle of electromagnetic radiation with no mass that carries a quantum of energy. That'll be important coming up. Here's my little photon. You see it there? I've got a red photon on the screen. Obviously that would be moving through space at the speed of light, but we'll get to that. Now, what if we examine that photon and we say, okay, we have light streaming towards our eyes, and let's say we're seeing red light, it wouldn't be just one photon. It'd have to be a whole bunch of photons, like maybe a whole stream of photons shooting towards our eye. How would we end up with a stream of photons? Well, that electron would have to be jumping up and falling back down and jumping up and falling and doing this so that you have a constant stream of photons shooting out of that atom. That's the only way we would be able to see it. But let's go ahead and zoom in on a photon. Of course, this is sort of theoretical and hypothetical, but this will give you a good understanding of the wave and particle duality of light. I'm going to take that photon and I'm going to zoom in. Now that photon has a certain amount of energy. That energy is expressed as a wave. There's actually a calculation I'll show you in a bit that shows the relationship between energy and a wave. So I can draw the wave inside of there to show that red light does have a certain wavelength, even if it's only one photon of that light. But let's say we have a stream of these particles or a stream of these photons. As I put all those together and I start to look at what that appears to be, that very much is the wave that we've talked about in earlier lessons. So if we do this whole thing in reverse, we can take the wave and look at the smallest part of that wave that has the properties of that light, of the energy of that wave. We call that a photon, and then we can boil that back down into the smallest part of light, which is a photon. And if we put a string of those together and just keep building this up, we end up with the wave of light that we've already learned about. So it acts like both, and it's important to understand it as both, because both things help explain how light acts. So recall, a photon is the particle of electromagnetic radiation. A quantum is the energy, or the minimum amount of energy that can be gained or lost by an atom. And if a photon has one quantum of energy, then that minimum amount of energy that can be gained or lost by an atom must be equivalent to a photon. The photon is the expression of that energy that's being given off by an electron. Now, let's go back to our ladder, right? The ladder is just my sort of explanation of if an electron tries to get farther away from the nucleus, the only way it can get further away from the nucleus is if it has more energy. So it'd have to absorb energy. And then we're saying, okay, if it falls back down to back down to its ground state, it's got to give off that energy. And this is why we end up the falling action of an electron back to its ground state gives off a different photon with a different amount of energy. That different energy gives off or is a different wavelength, so it's a different color of light, it's a different kind of light, and that's how we end up with the whole spectrum of light. So here's that formula I was telling you about. Okay, Max Planck, famous scientist, he's the one that helped find the relationship between the energy of a quantum and the frequency of the emitted radiation. Frequency goes back to the wavelength. The energy of a quantum is equal to h times the v, which is the frequency. Anytime I have a box on my screen, that tells my students this is really, really important. I need to put this in my notes because I'm going to need to use this a lot. The h is Planck's constant, which is 6.626 times 10 to the negative 34 joule seconds. That's a fun one to remember. I'll show you why it's joule seconds in just a moment. And if you're not aware of this, a joule is a measure of energy, okay? Which is good because we're calculating energy here. And V is that's a Greek letter, by the way, but that symbol represents the frequency. In my class, we call it the frequency, so we can remember what that symbol refers to. Frequency is measured in hertz, or waves per second, or hertz is anything per second. You could be counting cars going by on the freeway, and if you counted how many went by in 1 second, you could say 8 hertz for the cars. But in our case, we're talking about waves or photons per second. Let's break this down. What is the energy of a quantum of light with a frequency of 9.00 times 10 to the 20th seconds to the negative 1, which is the units for hertz? Through this little lesson, we only have one formula, right? That's E is equal to HV. So let's start filling some things in. Do we know the energy? No, that's actually what we're trying to solve for. So energy is going to be equal to, now we know this is Planck's constant. If you go and look what you wrote down, Planck's constant is 6.626 times 10 to the negative 34 joules times seconds. Okay, then the next one is the frequency. Well, the frequency is 9.00, so times 9.00 times 10 to the 20 seconds to the negative 1. Well, what does that mean? That means per second, right? Seconds to the negative 1 means per second. I'm going to write it like this just for a moment to show you why. Look at this. In dimensional analysis, in math, if we have seconds on the bottom and we have seconds on the top, well, don't those cancel out? If I just go ahead and get rid of these, then that should, oh, wait, look. The only thing we have left are joules. And that's what we need that's why it has that weird units, joules times seconds. Now all we need to do is plug this into the calculator and get our answer. So 6.626, we use the EE button because EE means times 10 to the negative 34 times 9.00 EE, because that means times 10 to the 20, and we hit enter. The energy of the photon that we're examining then is 5.9634 times 10 to the negative 13 joules. That's a small amount of energy, but it doesn't really matter. The point is that we can literally calculate how much energy is stored up in that little teeny tiny photon. That's pretty incredible. If I want to be careful with significant digits, this has 1, 2, 3, 4, and this has 1, 2, 3. That has 3, so my answer should only have 3. If you're unfamiliar with significant digits, I've got lessons about that. Just go to Beals Science School and you'll find them there. But there's my true answer with the correct number of significant digits. The energy of a photon is equal to the energy of a quantum. The quantum is the measurement, the photon is the thing, although it's not really a thing because it's just energy, but these two are interrelated. I mention this because if you end up with a question that asks you about the energy of a quantum, you use this formula. If you have a question that asks you about the energy of a photon, you use this formula. It will give you the answer for both. I've done a whole series of lessons about light, electrons, atoms, quantum, wavelength, and everything in between. I want to take one moment to do a quick review. What is light? We now know that light is a particle. It comes in chunks. What are particles of light called? This is where you answer out loud. They're called photons. How much energy do they have? 1 quantum. Each photon carries 1 quantum of energy. If we have a lot of photons, we have a lot of quantum. 4 photons, 4 quantum. And there's the relationship here, and we can calculate that, right? We also have learned that light is a wave. It's both. We have to be able to deal with it as both things because, well, both things explain how light works. We can measure its wavelength, and therefore we can measure its energy. We can measure its frequency. If we go back and we talk about what is the scientific name for all the types of light, not just the visible spectrum, but everything else, that's called the electromagnetic spectrum. Electromagnetic. What causes light? Oh, this is a good one. If you remember everything we've talked about, if an electron that's on the outside of an atom absorbs energy, it can't live in its ground state or its home. If it has more energy, it would have to jump to a different energy level further away from the nucleus. When it does, that's not its home. That's its excited state. And because of the configuration of the atoms in the electron, it needs to go back to its ground state. But it can't go back to its ground state unless it gives off energy. So it gives off energy, and we call that electromagnetic radiation. We call that light. This is where all of electromagnetic radiation, all of light comes from. Then let's try a practice problem that really brings together all of the things that we've learned about light, not just in this lesson, but in earlier lessons. What is the energy of a photon of light with a wavelength of 4.50 times 10 to the negative 9 meters? We do know a formula that has a relationship between energy of a photon is equal to Planck's constant times the frequency. Okay, well, let's do that. So energy is going to be equal to Planck's constant, which is 6.626 times 10 to the negative 34 joules times seconds, times the frequency. But wait a minute, we don't have the frequency. We're given the wavelength. Well, how are we supposed to do this if we're only given the... Oh, wait, we know some other things. Let's go over here. In an earlier lesson, we learned that c is equal to the wavelength times the frequency. C is the speed of light, is equal to the wavelength times the frequency. So could we use all of it? Well, yeah. All right, we know that c is the speed of light, which is 3.00 times 10 to the 8th meters per second. I'll write it like this. That is equal to the wavelength. Well, we know the wavelength here, 4.50 times 10 to the negative 9 meters times the frequency. Well, I could rearrange all this and solve for the frequency and put it up here. So let's do that. Divide both sides by 4.50 times 10 to the negative 9 meters. Divide this side by 4.50 times 10 to the negative 9 meters. Let me clean this up because this over this is going to cancel it out. I've got 3.00 EE8 divided by 4.50 EE. Remember, EE means times 10 to the, and I have negative 9. Enter. There we go. So the frequency is 6.67 times 10 to the 16th, and that's, well, let's do it here. Meters cancels, so we have per second. Per second is hertz, so we have per second. Let's put that up here. 6.67 times 10 to the 16th per second. Now, these two are going to cancel. We're going to be left with joules, and then we just need to calculate the energy. 6.626 EE negative 34 times 6.67 EE, which means times 10 to the 16th. And we get 4.42 times 10 to the negative 17. And what are our units? Joules. That's the energy of a photon if it has a wavelength of 4.50 times 10 to the negative 9 meters. It's really incredible. If you're following along here with this kind of math, that you can actually calculate the energy of an individual photon of light, well, we can go a lot of places with this now. Now that we understand that light has energy and we can quantify, we can measure, we can actually calculate that energy, we can start to look at this in real world applications. Like, how does a solar cell work? How does that absorb energy from the sun and make electricity so that our appliances and our homes can run? Well, that's called the photoelectric effect. That's where we're going to go next in our lecture. Lots of other things to watch. Come over to bealscience.com and you can learn all about science and chemistry and everything else, or Beals Science School on YouTube. Thanks for watching and keep on learning.